So now that we know how to add two waves via the vector addition and the phasor method, it's very simple then to scale this up to multiple vectors or multiple phasors. And the way that we do that is by simply adding them all together. We have to keep in mind though that the phase difference between each of these vectors has to be constant, and it's going to be equal to phi. So remember that at each instant in time, the projection of that resultant vector on the vertical axis represents the time variation of that resultant wave due to how all these other phases are being added together and how they vary in time. The phase angle, remember from when we added two phases together, the phase angle is between the resultant vector and the first initial vector that we're adding together. And the resultant expression of the projection onto the vertical axis is going to be given to us by ER, which is the magnitude of our resultant vector, sine omega t plus phi. So then the way that we work out the amplitude of them is you can simply do your vector addition, where we work out we add up all the horizontal components, and then we add up all the vertical components, and then we end up with the magnitude as well as the direction of our resultant wave. So I'll do an example now so you can see what I mean.
Okay, so we have an example problem here. We have three light waves that combine at a certain point where their electric field components are given by this. We want to find the resultant component, ET, at that point. So the resultant wave, ET, at that point is going to be given to us by this equation. E1 as a function of t plus E2 as a function of t plus E3 as a function of t. So we know at a certain point where they combine, the resultant wave is going to be the superposition of the three waves that are combining. So we are free to evaluate the phasors at any time t that we choose. So we are going to choose t equals 0 because that is the most straightforward way to do that. We can evaluate these straight away. So at time t equals 0, E1 is going to equal E0. So it's just going to be a vector E0 along the x-axis. It's not going to have shifted away from the horizontal axis. And then E2 is going to be E0 sine 60 degrees, and E3 is going to be E0 sine negative 30 degrees. Okay, cool. So what we can do actually is draw these waves. So I'm going to try and draw them now. So remember our first wave, I'll do them in a different color. So remember our first wave, this is going to be E1 here. And this is a vector and it is E0. It's got a magnitude of E0. So this is our E1 vector. Okay, E2 is at an angle of 60 degrees. So this is our vector E2. It's supposed to be the same length, so it has a length of E0. This is our vector E2, and this angle in here is 60 degrees. And finally, our third vector, E3, is at an angle of negative 30 degrees. So it's going to do something like this. Remember, we have to add them all head to tail. So this has a length of E0, it is E3, and this angle here is 30 degrees. Okay, cool. So our resultant vector then is going to look something like this. So remember this is what we care about is the projection onto the y-axis. That's because this projection onto the y-axis varies in the same way as a sinusoidal function. So as these vary in time, this projection onto the vertical axis is going to vary in time. So this is our vector here, ET, and our resultant vector. And its projection on the y-axis is going to be E. Okay, so the way that we add these up then is essentially we need to sum all of our horizontal components and all of our vertical components. So let's do our horizontal components first. I've just labeled it as x. So remember, in accordance with these angles, our horizontal components are going to be given by cos of the angle equals adjacent over hypotenuse. So the amplitude multiplied by cos of the angle gives us our horizontal component. So this will be E naught cos 0 plus E naught cos 60 plus E naught cos negative 30. And when we add all that up, we get around 2.37 E naught. Okay, cool. So that's our horizontal component. Let's look at our vertical component. And our vertical component, so if we just check out a triangle, it's going to be sine. It's going to be exactly the same, but sine, because remember, sine is opposite over hypotenuse. And when you do all that, you get about 0.366 E naught. Okay, cool. Now, to work out, so this is our horizontal and vertical components. Therefore, to work out what the magnitude is of that, we would just evaluate it like we would a triangle. So it's going to be 2.37 E naught squared plus 0.366 squared, E naught squared, and then the square root of that. And then when we do that, we get about 2.4 E naught. Okay, cool. So we're almost there. What we need is this angle here, this beta. So the way that we do that, remember, as we progress in time, all of this is going to rotate with an angular frequency around. So this beta here, though, we can still work out, and it's going to be constant. So it still makes a constant angle with the first phasor, but they're all going to rotate around as due to the angular frequency. Okay, cool. So the way that we work out the angle beta is the same way. We just have our two, so we can use tan in this case. So it's going to be tan beta equals opposite over adjacent, which is going to be 0.366 divided by 2.37. They're both E naught. Therefore, if we take the inverse tan of that, and you get about 8.8 degrees. Okay, cool. So then to write the equation in full, we would say E t equals E sine omega t plus beta. So now we can say ET equals, now it's our 2.4 E naught, 2.4 E naught sine omega t plus 8.8 degrees. And that's how you add multiple phasors.